First thing we're going to do is vote on the test. Moon, what's your first exam? I think we talked about this last time. Thank you guys for allowing that. I think that's pretty well. So, anybody want to make any suggestions for exam dates?
The Friday after spring break.
All right. Yes, sir.
Friday.
This Friday? All right. Let's put them up and then we're going to vote. All right. So, let's see. This Friday would be, is that the 3rd, March 3rd?
Yeah.
Friday. This is March 3rd. What else?
The Friday after spring break.
March 10th.
Friday,
Oh, my goodness.
March 10th.
This is going to be a tough quiz. Oh, shit.
You got another one? Let's do it.
No, 17th.
What's that?
17.
Not the
10th is during spring break. I was on there.
Yeah, I'm down. Online.
Online.
Ooh. Anything else? Any other day? We're going to vote on this, so the top two, we'll just have a runoff. Anything else?
Maybe the Wednesday after that, 22nd.
Wednesday, March 22nd. All right. Okay, here's the way I'm going to do it. You count with me, all right? We've got to make sure this is legit. And everybody looking around. So you get to vote one time. Put your hands up if you want it on Friday, March the 3rd. We'll do a runoff. 1, 2, 3. I see 3 hands. Not very promising. All right? So now, Friday, March 17th, 1 hand. I'm going to just say this, it looks unanimous. Okay, that's the date. Everybody with me? Nick, send me an what? Nick, send me an email. Tell me that. I'll put it on the calendar, put it on OneNote, make sure everybody knows. That was painless. Now, sometimes they get real close and then you hear arguments in the class. All right. I just hope there's no basketball game that all of a sudden appears. Because I had that happen one time. And all of a sudden, everybody's going to a basketball game. This is during the season where we ended up in the semifinals. So I don't even know where that is. Okay. Questions about the homework? Anything? I gave you a bunch, but it was fairly straightforward. If you listened to that lecture online, I think you were pretty straight about this stuff wasn't bad. At least 1 or 2. Did you get that Yachty online or not? You got it? Okay.
Can we do 3.52?
Yeah. Tell me what it is.
The typical length of a piece of jumper wire on a student's proto board is 5 centimeters.
This is wire, okay? So we got 5 centimeter long wire. Go ahead.
Assuming AWG 20 with a wire diameter of
Go ahead.
0.812 millimeters.
A diameter
Copper
equals-
wire,
Yeah, all right. Point what?
812 millimeters.
812 millimeters, all right. That's diameter.
The
It's copper.
The
Right,
first,
sigma of copper, by the way, is about 5.8 times 10 to the 7th. This is 101 meters of Siemens per meter. I gotta make one comment. I put up a table just before class. I mean, a link to a table on OneNote that has all the actual conductivities, and one over that's resistivities for common metals, all the way down to nickel, brass, everything. So, what are they asking?
the first part asks for determine the resistance for the length of the wire.
All right, so this is a constant cross-section wire. Do you all agree with this, class? You remember on Friday, I said if you have something with constant cross-section, you want the resistance. This is a DC resistance. It's just going to be length over the conductivity divided by the cross-sectional area. How many remember that? Proportional to the length, inversely proportional cross-sectional area, inversely proportional to the conductivity. For this one, it should be straightforward. So that means the DC resistance for this, the length is 5 centimeters, or 0.05 meters. Conductivity is 5.8 times 10 to the 7th. And then the area is pi a squared, if it was in if it was the radius, this is diameter, so it's gonna be pi times the diameter squared over 4. So here we're gonna have pi, and then its diameter, which is 8.12 times 10 to the minus third squared. Square, it's divided by 4, so I can multiply by 4 up here, and that should give you the resistance. What is it? I mean, this is straightforward. I think everybody sees this. It's just simply applying basic math.
It's 1.7 milliohms.
Is that right?
Oh, I was just saying what that was the answer was.
1.7 milliohms. Is that the right answer? I mean, is that what you looked up, the right answer? Or actually did the
That was
calculation?
the right answer. I've not done the calculations yet.
Just do the calculation. They can be wrong in the book. Are you getting that, guys? Anybody?
Yeah.
You getting it? Okay. All right, I'm giving you that. What else?
Determine the power dissipated in the wire for 10 milliamps of current.
All right. Now, this is one of those things, you can go the long route where you get the power density at a point and then multiply it by the volume. Or you might as well just do it the old-fashioned way, V times I. Y'all follow me on this? Or I squared R, right? This is DC, so if we want the power of this wire, it's just I squared times R. That's going to, how many milliamps?
No, 1.7. Oh, I'm sorry, 10 milliamps.
10 milliamps? So it's going to be 0.1 or 0.1 amps squared times the resistance, which is 1.7 milliohms. That's 10 to the minus third. And what is that? That's going to be, this is 10, so that's 1.7 times 10 to the minus 5 watts, or 17 microwatts. Is that right? Is it? I mean, is it?
The answer says 170 nanowatts.
Did I do something wrong here? You said it's what, 10 milliamps?
10 milliamps.
Oh, not bad. Oh, 1 squared. Yeah, that would be. Yeah, that would be, that's right. My bad on that one. I'm sorry about that. What else? Anything else?
That was it for that question.
That was a pretty straightforward, basic question. You got another one for me, anybody? Didn't I give you stuff that had different, like, spherical and cylindrical kind of resistance?
Yes, can we do 3.51 instead of 2 spherical conductive shells?
This is a good one. Spheres and cylinders. Good. Hint, this is a good one. Go ahead on this one.
Okay, so we have 2 spherical conductive shells, one with radius A and B. B is greater than A.
One radius A, one radius B. Go ahead.
And then they're separated by material with conductivity, the sigma.
We got our, and we got
What does that say?
sigma is what?
It doesn't say.
Okay, go ahead.
And find an expression for the resistance between the 2 spheres.
We did this one. How many remember doing that? All right. Now, the way you do it is important to notice this. If we want the resistance between the inner and outer conductor, just assume this one's hollow. And it's got the metal on the inside, metal on the outside here. We're trying to find the equivalent resistance here. So the steps are, you assume I. From I, you get J. Once you have J, you get E. Once you get E, you get B. And finally, you get R is equal to B over I. Now, I tried to make that clear last time. This is something you assume a current. Y'all with me? We're going to assume the current is placed, I mean, you could think of it this way. Bore a little hole through there, put a wire, metalize the inner surface. There's going to be a battery, has current I going through, has a voltage V, and the outer layer is grounded. So we assume I. Now I need J. This is important. This is cylindrical, right? I mean spherical. If it's spherical, all the current that comes out of radius A and is moving this way is going to flow to the outer surface here, all of it. And it's going to go through concentrically large spherical surfaces. If you put an imaginary spherical surface out here of a radius R, you're going to get that current density by taking the actual area of this. So it would be I over 4 pi R squared AR. That would be the current density, J. You all agree with that, class? Remember me doing this one, if you were online? All right, now what's the next step? After J, what do I get? E. How do I get E?
Divide by epsilon.
Simply take J divided by sigma, right? So it's going to be I over 4 pi r squared. I'm using a capital R here, but it can be smaller. Divided by sigma, which is a constant here, in the AR direction. Now I have the E field. What's my final step?
Divide by.
Voltage, right? We have to calculate. And how do we calculate the voltage?
Divide by R.
Integrate between the inner and outer conductor, right? We're going to integrate this. Now, here's one tip. Don't worry about the signs. It's going to be a strictly positive value. It can't be negative. This is a passive resistive element. So when you integrate this, the integral of E dot dl from A to B really becomes simply the integral of I over 4 pi
3.51.
sigma r squared AR.
Yeah,
And
3.5.
dot dl is simply dr AR. So the AR's dot out and you get from A to B of this, take an absolute value of that too. That means over here when you do it, you all follow me what I'm doing? I'm doing a simple integration. I have a 1 over r squared dr type of integration. That's minus 1 over r, right? And we're going to take the positive component of this. When we evaluate this, you're going to see that the value of the voltage is simply going to be equal to 1 over 4 pi sigma, and then it's going to be 1 over A minus 1 over B, assuming A is smaller than B, where B is greater than A. And that's the resistance. Y'all follow? That's the voltage. To get the resistance, this is I here. To get the resistance, we divide that by I, and now we get the resistance. That's straightforward. Here's one cautionary note. If sigma wasn't a constant, but it was only varying in the radial direction, then at this point, right here, we can have this be a function that's different than 1 over r squared. It could be if sigma was just, say, proportional to r, then you would have sigma over r cubed kind of deal. But you all follow me on this? So you have to be careful. If sigma varies radially, you can still do it this way. But you have to be careful with that last integration of E dr. Okay? Yep.
So if it varies radially, you just leave it in the integral and integrate it like
Well,
normal.
If this varies radially, right here, sigma varies radially, then sigma r, you have to tell me how it varies, because here I have r squared times some other function of r. If it's linear, it's proportional to r, it would be 1 over r cubed here. But just as well, it could be proportional to 1 over r.
Okay.
And you don't know what it is. Do y'all follow me? So that's the cautionary note. All right, any other thing on that problem? You ask me that.
And that covered everything as far as finding the actual expression.
Okay. Good. All right, now today, I want to just tell you what I'm planning on doing. I'm going to get through all this before the quiz. The next section is on dielectric materials. It's just material that is a good insulator but can store electrical energy. We'll talk about this. Then we have to do boundary conditions, and we have to do the actual Poisson equation too. This comes before we do capacitance and Whitworth's book. I'm going to take you through this in a way I think is most meaningful to you, and will probably answer a lot of your questions. Now, everybody here has had, you've had this already in physics, and he probably didn't talk a lot, your physics teacher, about a lot of the different materials and why the permittivity is so important, But there's two real things I got to talk about today regarding these dielectrics. I call them insulators. So if you look in your book on page 183, it gives you a picture of what's going on in a dielectric. Now, a dielectric basically has no conduction current. In other words, if you painted an electron, and that electron was in some way, shape, or form located on the surface of a dielectric, it can't flow through to the other side. Effectively, it can't. Some do, but it's a small amount. But you do have something called polarization current, And that's where the little dipoles get stretched. So if you have a dielectric, this is a simple explanation. It's going to be made up of things that are dipoles like this. Now they have two charged centers basically, but they're frozen in the lattice. They're not going to be able to move. The positive can't move away from the negative. Y'all follow me on this, class? But what can happen is, if I put an electric field, superimpose that electric field in the dielectric, they'll stretch. It's like a little spring here, and all of a sudden this thing's going to stretch, and there'll be negative, and that stretching is storing energy, just like a spring does. Do y'all remember in physics where they talked about the spring constant, like K delta X was equal to the force, and the energy would be 1/2 K delta X squared. If you remember this, K is just a spring constant. Well, the more they stretch, the more energy they store. But there is a limit where all of a sudden they can't stretch anymore, and one of two things happens. Either you get something called dielectric breakdown. That's where these things just, all of a sudden there's an arc through the material, it's like lightning hitting you. That's dielectric breakdown, or it goes through a phase transition from one material to the next. And I'm not going to get to the phase transitional stuff. That's well beyond our class. However, y'all have seen, have you guys destroyed capacitors either intentionally or by accident? Hear that arc over thing? That's when you see the dielectric breakdown strength of the material. Do you know what the dielectric breakdown strength of air is? What would be the electric field that would be necessary to break this down? It is an electric field value. If we had two plates separated by 1 meter, how large of a voltage would it take? Any guesses? Some of you may know. If you're an electrician, you probably do. It's 3 million volts per meter here at sea level, right here, all right? Now, it varies tremendously depending on the pressure. As the pressure goes down, the dielectric breakdown strength goes down as well. It takes less on it. But it's real important with insulators that they have a very high dielectric breakdown strength. So you can put a lot of voltage, therefore get a lot of electric field between two conductors without it arcing over. Now the stuff that you see usually with extension cords, these are types of plastic or rubber insulators. They're not bad, but they're not that great. If you really want incredible dielectrics, they're exotic materials and you can get them, but they cost a lot. The reason dielectric breakdown strength becomes a real issue is when we're trying to pack microelectronic devices into smaller and smaller structures. A couple of volts difference when you have 10 to the minus 6, 10 to the minus 7 meters of spacing gives rise to voltages or electric fields that are in excess of the breakdown strength of a lot of common materials. But remember, we want very dense, highly packed things. Another thing happens is when you try to get anything out of an antenna system and the electric field exceeds the breakdown strength of, say, air, if it was just air, say, in the inner part of the antenna, well, that's no good. But you would like it to be able to take have an enormous amount of power coming out and then into the atmosphere just at the threshold of breakdown. This is where these exotic materials come in, and there's a lot of stuff that they use to prevent breakdown. So that's the theory behind, at least, and it's a very hand-waving theory. We don't go in through all the crystal chemistry. When I was in graduate school, I went through crystal chemistry, and we had to go through all the reasons for this and mathematically formulate what the dielectric strength would be and all the other electrical parameters going through first principles. It was a long but interesting thing, and it gave me a lot of insight to that. So here's what you need to know as engineers right now. You need to know that in general, when you have a D field, it's equal to epsilon times the E field. That's the general form you see. Well, epsilon is epsilon naught times epsilon relative times E. I can also say that this, now Whitmer's book does this, and I don't worry too much about this. He'll express this as epsilon naught, and it's going to be 1 plus something called chi. It's the electrical susceptibility times E. This is in his book, and he'll talk about the polarization. This is still B. The actual D field will be equal to the polarization field plus epsilon naught times the E field. Now he has this in his book. This is on at page 183. I don't want you to focus at all on this right here. This is something material science people worry about. We don't need to do that right now. We don't even need to do this. We need to do this. So when we talk about dielectric materials, we worry about epsilon relative. That's what we want to know. Now, epsilon relative of free space, or without anything, is about that what it is for air. Epsilon relative is 1. It can be, theoretically, it can be less than 1, but that goes into another direction we don't need to go. It has to do with things that are allowed to happen only because of some other energy storage mechanisms, and I'm not going to go there now. So epsilon relative has a range of about 1, and it goes all the way up to 40, 50, 60,000 for exotic materials. The typical range is from 1 to about 4. Maybe 5 for some materials. That's about the range. Does anybody know what the dielectric constant is for like mica, anything like that? How about the simplest insulators? You can look it up, but it's somewhere in the order of 2.2. Not a huge, big difference, right? But that value of epsilon relative will tell you that they can store more energy than air by just that much. Now, I'll tell you exactly, I don't want to go too far afield in this, but when we talk about energy storage, this you need to write down. You know, we talked about the power density, the sigma E squared on Friday. Remember that? So, if we talk about power density, put it down. That's equal to sigma times magnitude of the E field squared, and it's in watts per meter cubed. When we talk about energy density, and sometimes you'll see WE here, that's going to be 1/2 epsilon magnitude of E squared. He gets that from 1/2 B dot E. But this is the one I go for all the time. It's 1/2 epsilon E squared. Now, epsilon is epsilon naught E squared. You all follow me? So hear me on this one. If you think about this, the power density is equal to 1/2 epsilon naught times epsilon relative times magnitude of the E field squared. Look at this for a second. If it was free space, this energy density would be 1/2 epsilon naught E squared for a given E field, right? What happens as epsilon relative goes up? Well, the ability to store energy goes up proportional to epsilon relative. It's linear related. So if you have a material, how many have heard of exotic capacitors in here? Anybody? Or they call them supercapacitors. Have you heard of that at all? All right. Supercapacitors can store an enormous amount of charge with a small voltage difference. And for instance, you can melt a penny. You charge one of these up. If you take a penny and put it across it, some of these at least, it'll melt the thing. All right? It's got that much energy. That's a lot. The reason they were of interest to a lot of places is because with car batteries, what's the problem? It gets cold. You try to start your car, it won't start, right? It can't get the current out. There's something called the cold, or really it is the cranking, the peak amp cranking power a battery can do. Well, if you have a capacitor, a supercapacitor, in parallel with your battery, it's not really bleeding anything through there or discharging your battery, but it can store a tremendous amount of energy. So when you turn the crank on your car engine or whatever it is, it needs to take a lot of current. A lot of that current can come from the supercapacitor, not the battery. Do y'all hear me on this class? So that's one of the interests that the automobile industry had and a lot of other places. Those kind of materials are exotic materials. They're expensive, but they can make that dielectric constant go way up. And if you look up the supercapacitor and see the dielectric constants, I think they get up into the range of 50,000, but I don't know it for a fact. I'm not a material science. So that's some of the interesting things. Now, when we talk about dielectrics and their effects on things, this is really it. Just that. That's the only thing you need. This epsilon relative times epsilon naught times the E field. That is the D field. And that's it. That's how easy it is. Now, do you all remember hearing something like this before, right? I mean, do you remember permittivity or dielectric constant, however they termed it in physics? Just show of hands, how many remember at least being exposed to that? Everybody should have been. If you haven't been, somebody didn't do their job. Now, I want to show you what we need to do with that to figure out how to calculate capacitance and other things. So, next thing we talk about in the book are going to be boundary conditions. And this is on page 186. So these are electrical boundary conditions. Normally they just call this boundary conditions. What are they? Well, I'll tell you what they are and then I'll prove this. The first is that the tangent electric field, E tan 1, is equal to E tan 2. It means that if you have materials, and this is material 1, this is material 2, here's a perpendicular that I'm showing you there. This could be air, this could be water, it doesn't matter. When I say tangent electric field on this side, this would be E tan 1 is parallel to the boundary, and on the other side, this would be E tan 2. They have to be the same. Anybody want to take a guess why they have to be the same? Absolutely have to be the same always. All right, think of this. Without going into all the detail, suppose I have a little contour like this. This is just a construct. It's an abstract concept. And I have an electric field on this side. It's tangent to this. An electric field on this side. Call this E1, E2, both tangent. And this is the height. Now, if I started, I'm saying that there is an electric field on this side, electric field on this side. We're only worried about the tangent component. I can put a P here if you want me to. But if I start at this point and integrate around that closed loop, what do I have to get? So let me ask you this. What is the integral of E dot dl from A to A? Well, that's VA minus VA, right? What is that?
0.
It's 0, right? So the integral of the electric field around any closed loop is 0. If I start here, and I'm going this way, the only field I have is the electric field that's tangent, right? The length here is irrelevant. So if I come up here and integrate, I get this E field times the height or length here, right? Come over here, I'm making H go to 0, so there's no contribution there. Then I come down here, the only way it goes to 0 is if the field on both sides is the same. Does that make sense to people? And I'm trying to make just very easy arguments. It has to be the same, or else you would get something that isn't 0. And it must be 0. Y'all follow me on this, class? By the way, that's true for the actual total amount of work done in any conservative field. For instance, with gravity, if I take and I look at the actual work that gravity would do on an object, and I start here and I move it around a closed path and back to the same point, the amount of work done is 0. Right? Now, in truth, you expended some energy to get it up there, but theoretically, you got it all back when it came down, and then you expended more to get it there, but the net sum will be 0. Now, that's a conservative field. There are non-conservative fields that we'll talk about where that isn't the case. So that's the first thing, E tan 1 is E tan 2. The second is the normal component, the D field, is the same on both regions, in both regions, except if there's a charge density. So what that means is the normal component, D normal 1, is D normal 2. So if this is region 1 and this is region 2, the normal component of the D field, the region 2, is the one that's perpendicular to the separational boundary. Do you all follow me on this class? And the D field here would be equal to D normal 2. Y'all with me? Now that is true unless there's a surface charge between the two regions. Then things change, and I'll explain why. And I'm trying to do this in a way that's simple. I don't want to get too complicated for mathematics. Let's assume I have a charge density here, right? Just on that surface. Now I'm going to build a little pillbox, if you will, like so. all right? And it's gonna have an area here, A. And it's gonna have a height H, or I should say, the height is gonna be in that direction. If I take the limit as H goes to 0, what I really have, and I look at this thing just for a moment, just think about this. Remember Gauss's law, it says the integral of d dot ds over any closed surface is 0, correct, class? So if I look at this, forget this for now, just take a look at this. So that means the integral of d dot ds over closed surface has to be the charge enclosed. Well, the charge enclosed in this case would be rho s times A, the surface area, whatever it is, times A. That's the amount of charge. What is that equal to? Well, that's equal to the actual normal component of the B field, and it would be pointing this direction, this way, this direction, this way. It's going to be that, or twice that, times the area, where you can see D normal is equal to rho s over 2 for a given surface charge density if there's no other conditions. Does that make sense to everybody? That would be the normal D field if there was a surface charge density that was between those two regions and no external D field. Does that make sense to everybody? Now, but I'm not going deep into the math. I'm trying to make this understandable in a general sense. Now, if there is an external field, I just want to explain something. If there is an external field, then you would have to account for the external field's reduction of the D field on this side and enhancement of the D field on that side. Do y'all follow me? You would have to do that. So the way Whitmore's book does it, you can do it a lot of different ways, but this should make sense. If you have a region, I think he does it like this. He calls this region 1 and region 2, and he uses a unit vector, A21. All right, this is on page 188 of your book. And it's actually equation 3.110 at the bottom of that page. He's going to say that if I have this as a unit vector from 2 to 1, if I take A21 and dot it into D1 minus D2, that will be the surface charge density. And he shows this on the top of page 188. And he shows the regions. Now this can be it can get you a little irritated. This comes from basically doing what I said over there mathematically. This is the point form. I try to show you the integral approach to it, but you'll get this the same way. This is, one of those things you're always trying to think about. Which way does the unit vector go? Well, I'm not going to push you on that one. I'm going to tell you that. I will tell you right now that I don't plan to have surfaces with bound charge density or anything like that I'll give to you with your problems. I just want you to be aware of this, all right? Unless it's the midterm, and I'll tell you ahead of time what's coming. Now, just out of time, but last thing I wanted to do, we'll do some of these boundary value problems, but the next thing is I want to talk about boundary value, and then I'm going to give you some homework for Wednesday. Now, please do this homework. Are you okay with everything I'm showing you? You're going to see that it's not hard to do these problems. It really isn't. Last thing I want to show you today before the quiz is this. You remember how we had this? Divergence of B is equal to rho V. You all remember that? What's that called? Anybody? Begins with a G.
Gradient.
Freudian.
Gradient.
It's Gauss's law, isn't it? The point form of Gauss's law? How many remember that? You at least saw this, right? Now, if I say D is equal to epsilon times E, then I could say divergence of E is equal to rho V over epsilon. Y'all follow me? And I just substituted in epsilon E for D. Y'all follow me in that? And then divide by epsilon. Now that works. Now, you also get that E is equal to minus the gradient of the voltage. Y'all follow? That was something we talked about, right? And because of that, if I plug that in here, Now I get del squared of V is equal to minus rho V over epsilon. And this is Poisson's equation. If it was equal to 0, it would be a charge-free region, and that's called the Laplace equation. If you look in your back cover, you're going to see a del squared operator for cylindrical, spherical, and Cartesian coordinates. At the very back page, probably in the bottom. You see it? Del squared. It's called Laplace. How many see it? Got it? Y'all see it there? Back cover. All right. That's simply a second-order derivative. Today, I don't have time to go through that, but I'm going to give you your quiz. I'll give you some problems. I don't think you're going to have a lot of trouble.